Hi there. It was about 6 years ago and my knowledge of REST microservices and the surrounding patterns was pretty rudimentary. We just put a national scale system in production and it kind of locked up. I thought, why? Well, luckily we had a really good logging and monitoring system in place using Splunk, so I managed to do some root cause analysis. And the front end service was calling a business service, which is calling an integration service, which is talking to a back end system that had gone down. A lot of these requests had come in, each waiting for a response from the external system, and very quickly we became thread starved and the service completely locked up. I mean, that was a big fail. We'd basically built a distributed monolith. And today I'm going to try to explain to you how you can avoid my mistakes made in my hubris when I was much younger, many years ago. And in order to do that, we'll be discussing microservices using event-driven architectures. Warning, I have stolen one or two of these diagrams to complete this deck, which leads to a further warning that there are diagrams. So, I'm going to start with, well, in this case, your mileage may vary. This is a grab bag of patterns and concepts that you may use on a case-by-case basis. The example architecture shown at the end is just to show you how it could all hang together if you use them all in concert. So what we're going to go over today is what a microservice is, some patterns and anti-patterns. We're going to cover data and transactionality, some of the challenges we've faced along the way, and a kind of an example architecture. So true microservices, well, what do they give us? Well, they give us independent deployment. This is one of the key things. This means we can deploy our services completely separately. This means we can take parts of the overall ecosystem in and out of service quite quickly. It makes our deployment small. We only deploy what we need to do. It also allows us to do independent scaling, which means that we can take an individual microservice and put elastic scaling on it, or actually reserved instances on it, without having to scale the entire architecture up and down. If you have a monolithic architecture, then scaling up and down can become very expensive very quickly. Also, and this is probably one of the hardest topics, is it has independent data. We'll go into that pattern shortly. And a true microservice, and this is where a lot of people get it wrong, is it's a decoupled and encapsulated design. It kind of follows almost like the solid principle for design, but in a service fashion. It means that the services feature low coupling and high cohesion. They also have what we call a shared nothing architecture. This means that we shouldn't be sharing code between them. This doesn't go for things like libraries and open source libraries and things like that. So obviously some things will be shared, but actually when it comes to application code, nothing should be shared between them. They allow for an evolutionary design. Microservices mean you can actually do some of your design up front, and as long as your actual core microservices design patterns and architecture are solid, you can add to them over time. You're not forced to do all of your design up front. Each one should be single responsibility, meaning that you do one thing and one thing well. When they start doing more than one thing, it means usually you need more than one service. And I think one of the key things that people don't push enough is really microservices should promote a kind of more product-focused thinking of services over individual projects, meaning you should be able to use microservices between different offerings, between different more traditional projects. But the main thing actually microservices should give us is agility. But they bring quite a lot of pain as well. Because they're distributed, because they use the networking, they increase call times. They also, because you are deploying more different services, they actually introduce increased operational complexity. And because you have to start thinking about things in a more distributed fashion, they introduce more design complexity. A monolith can, by its very nature, can be very simple. It has very little in the way of traffic, has very little in the way of design. It's easy and simple to put together. But one of the more difficult ones to approach is actually, there's no concept of distributed transactions of microservices. We had that in traditional SOA approaches, but not so much in a modern web-enabled time. And due to this lack of transactions and distributed the way of thinking, you don't get immediate consistency, you get eventual consistency. And because quite often you need multiple services to just do a simple thing like maybe getting some information for a web page, you might end up doing a lot of different read actions just to service one user. So what we're going to start with is some patterns and anti-patterns of microservices, and we'll have a little look first at some patterns, and we're going to go into some of these in more detail later on. So, I mean, one of the key ones is message brokerage, and we'll explain that. Orchestration and choreography, they're very much in the eventing space. Database per service, now this goes into the independent data quality of microservices. This means that basically you have an entirely separate database for each individual microservice, which means you can't have things like referential integrity between them, and this causes a lot of design confusion quite often. Also, we have things like the idea of a read model, the idea of keeping a separate store just for aggregated reads, and this leads into things like API composition, the request reply over request response. Request response is by its very nature synchronous, but request reply is an asynchronous version of that effectively. And we have commands and events, and we'll go over the difference between those as well. And something called CQRS, Command Query Responsibility Segregation, and it's an attempt to get around the issues with the API composition pattern. And then we're going to go into sort of some more, slightly more advanced topics, event sourcing and the Saga Pattern. So, what we'd like to do first actually is have a look as kind of far away from microservices you get. And this is the monolith. This is the very traditional architecture. I mean, if I drew a web box above that, it would just be a 3-tier architecture. Some of the problems with that, well, reusability is low to none. It's project rather than product focused. It will probably be locked away behind somewhere. There's no independent deployment or scaling. The data store itself, because you're sharing one data store, can become very unwieldy and query bound. However, this is a very simple architecture. Transactionality is simpler. Access to data can be from one central store. You don't need to do any data duplication. It means the actual storage is quite lean. It's a simple design, but monoliths are kind of a product of an age where we kept most of our processing in close proximity, often on the same box or with little network communication. That worked then, but using the same model in the cloud in a modern environment is kind of, with this high degree of networking, is like using Steam era technology to power Ferrari. I mean, you could, but it's not really the optimal solution. But for actually small projects, this might actually be fine. If you're doing something very small, you might just want a monolith. However, in the industry, when we're working with clients doing enterprise scale implementations, this is not really sufficient anymore. So distributed monoliths, this is probably the bane of microservices because they look a bit like microservices and people think they're doing microservices. But with the coupled deployment and scaling, it requires a whole service to be stamped out in each set of containers. It's not really much better than a monolith. In fact, operationally and design-wise, it's more complex. It's the worst of both worlds. They miss out some of the key points of moving to microservices. So you can crudely scale a distributed monolith. It's just not necessarily a good state to be in. It's expensive and it limits agility. This is where most people fail. Here's a diagram I've shamelessly stolen from Gartner. There's a step between them. There's also between what they call macro services, the monolith, there's something called mini services, and they're a subset of the distributed monolith. They give us some independent deployment and independent scaling, but really they still end up with shared schemas. They don't allow us to deploy database changes independently or independently scale the data stores. So they're not quite a monolith, they're not quite a microservice, but again, might actually be a solution if you're on a sort of a medium-sized solution. But really, if you want agility and independence, then this is still kind of a fail. As you can see there, the arrows show, well, if you're going towards the left, towards the monolith, you lower complexity, easy to run. And with this looser coupling towards microservices, you get your greater agility. And this is the kind of fail that I've fallen into before is the idea of call time coupling microservices. So you might have services that kind of look like they're independently scalable and deployable, but as you can see in this diagram, well, A calls B and waits for a response, but B calls C and waits for a response. So by actually calling out using synchronous HTTP requests, we actually bake in the fact that these services have to know about each other, which they really shouldn't do. So we've actually increased operational design complexity, but taken away some availability, really. So the logical separation of layers is great, but really, when you're doing microservices, you shouldn't be making out-of-process calls where you can help it. You should try and look at the service as one atomic business entity, which must implement everything to achieve its desired business functionality. As soon as you move out of process, you're in the hands of the network gods, and they're kind of unpredictable and capricious, and they can lead to quite a lot of failure. And this is another quite common pattern, is what we call the round-robin death spiral. Basically, if you've got a service A that calls a downstream service and it's behind a load balancer, where you think, well, okay, if one of those 5 services go down, that's fine. And that is fine if you're making a single call, but if you're making, say, repetitive calls to something like a reference data store, where you need to get several data sets, then basically as your number of calls goes above equal to or above the number of services, one service going out of use can actually cause the whole chain to fail, which means you can take your availability down to 0 quite easily. You can use retry logic to get around this, but it adds complexity to the code. So this is another downside to the coupling of services. What I'd like to do now is talk a little bit about data and microservices. And the main one is database per service. It's the hardest problem. So it's really kind of easy to understand. If you've got a database per service, it's great. You have your independence. But then, well, what happens if you need to get data from another service without using a HTTP call? Or if you need to actually write to another service and kind of have some kind of transactionality, suddenly things get complicated. And if you're moving between different schemas, well, what do you lose? You lose referential integrity. You lose ACID semantics. We know that direct calls are a bad idea, so how do we deal with data? Well, data consistency across services, I mean, you could use two-phase commit, which we'll go into in a minute, but really that's not really a sensible option for an event-driven architecture. So actually, going fully event-driven, using an eventually consistent approach, actually is a more sensible way of approaching it. Each service should be publishing an event when it needs to update, and actually maybe even considering its own read model. So here's a typical two-phase commit. It's a well-known algorithm, and it kind of tries to achieve the benefits of ACID, but the handling of two-phase commit is not that simple. It's 2 stages. It has a prepare and a commit stage. So the idea is you prepare everything, and then when it looks like it's worked, you issue 2 commit statements. But the problem is there's no mechanism to roll back the transaction if one microservice goes unavailable during the commit phase. It really doesn't solve the problem, and you still have to wait until the slowest resource finishes its confirmation. So we can't just place an order, update the customer, update the stock, send delivery through in a single ACID transaction this way, not sensibly anyway. In microservices terms, this is sometimes called try, confirm, cancel, which does actually have an element of rollback in the pattern, but it just doesn't work very well in a very complex ecosystem. So what might work well instead of a traditional transactional approach? We'll kind of get to that shortly. So there is one thing though, if you are going to be eventing, which we're going to discuss, there is kind of an atomic requirement. And when you're creating an event-driven microservice, we need a foundational kind of transaction. It's one where we can write to our data store, or whatever it is we're storing things to, and then guarantee that our event has gone out onto some kind of reliable messaging platform. So basically the idea is you write to the database, you forward the event. If the second fails, then you roll back the database transaction, and frameworks will typically kind of help you deal with this. Now, really, in reality, message brokers tend to be pretty reliable, so rollbacks on the second stage will be pretty rare. And this atomic requirement for events, it will be used in conjunction with some of the patterns we'll be using later. So kind of a quick sidebar for those unfamiliar with some of the underlying mechanisms for providing eventing. I'm going to quickly go over some of these. Basically, these eventing mechanisms provide the decoupling in our architecture. All of them share the quality that there's some kind of intermediary who's dealing with the event that doesn't really care much about the event itself. It kind of stores it in an ordered structure of downstream services to process, but really it doesn't mind too much about the format or what event it is. Now, we refer to these intermediaries as message brokers usually, and that decouples the processing of what's going on in service A from what's going on in service B. They do add some kind of overhead, all of them, but in the cases of some of the lighter messaging queues, this is actually a very small overhead. So in reality, although it does add an overhead compared to the actual amount of processing you'll be doing, unless you're doing in a very low latency environment, actually this is a very small deal really. So queues. Queues are probably one of the simplest forms of actually putting things onto a message broker. Basically, producers and queue messages, which go into a first in, first out queue, just like a regular queue. The consumers usually consume the next message by dequeuing it. Message may only be consumed once. This kind of makes it a little bit synchronous, but it does allow for parallel processing. So if you're using something like JMS, it almost acts like a load balancer for consumers if the consumers are actually doing a lot of work. It's great for point-to-point processing, where every message must be processed exactly once. Most good brokers include guaranteed delivery and persistence, so if you publish a message, it'll be in the queue for processing. You can be fairly sure that that's going to happen. You've got guaranteed delivery. Now notice the use of the terms producer and consumer. This is the terminology of a queuing system. So if you're using something like AWS, a good example of this is SQS, the simple queuing service. And then there's the next kind, which looks very similar. Diagrammatically, looks very similar. Almost the same diagram, is the same diagram because I copied and pasted it. But notice the terminology here is publisher and subscriber. So in this case, we have publishers who publish the topics that look a bit like queues, only the messages aren't dequeued once they've been processed. Multiple subscribers can subscribe to a topic. They usually keep some kind of pointer to the last message they've seen. So if they go down, they can catch up or rebuild. This means each message on a topic is expected to be processed multiple times. This is expected behaviour. As with queues, you can get some guaranteed delivery on the publisher end. If you're using AWS, an example is the SNS, the Simple Notification Service. Again, really useful if you want to do simple publish subscribe model. But the semantic difference in a queue and a topic is you can think of them as using commands and events respectively. So the first type is a command, and that's basically telling somebody to do something. So if you actually want a microservice to do an action, then you might issue a command. Say we'll say ship order or complete order. That has a very command kind of feel to it. And often the producer doesn't really care about a response. I mean, he cares that the message is being queued, but he doesn't care about the response. So he can do what we call a fire and forget message. This frees up the producer from waiting around for a reply. If a reply is needed, rather than doing the old request response pattern, we actually sit and listen on another queue for using the request reply pattern. So there'll be some kind of reply queue. So taking the other scenario is the event. One microservice announced an action has occurred. Say we'll say order completed or order cancelled. So actually semantically they sound a little bit different, and this is actually this means that you're saying that something has happened, not you're asking for something to happen. And when something has happened, other microservices, if interested, can kind of react to that event. And that's kind of a two-step process as well. As you publish an event to the message broker, and then any available interested microservice can pick that up by subscribing to the topic that it's publishing to. So that's kind of the core difference between the two. They're very similar patterns, but different. But then there's a third mechanism that's become really popular nowadays, and it's called data streaming technology. I mean, it's taken off lately quite a lot, with many large-scale projects adopting Apache Kafka and other technologies. But there is a significant difference to them. But I mean, if you look at a simple diagram, it doesn't look very different. I mean, if you're using SQS or MQP or something like that, you expect it to be fast. But queuing and notification systems don't tend to be capable of dealing with large volumes of data unless you have a very, very large message broker instance. But the thing about message broker is quite often SQS and SNS are almost no setup or maintenance. They're pretty low maintenance mechanisms. They have limitations on things like message sizes, but they also have different kind of notification routes as well. So SNS can do email, SMS, HTTP. In something like Apache Kafka, really, it's about a consumer subscribing to its data streams, and managing a Kafka instance is way more operationally complex than SQS or SNS. It costs more to run, it takes a lot more storage, and there's more latency by default because everything is durably committed to disk before streaming. So it's not an insignificant amount of time, and it might mean that actually something like Kafka is not suitable for low latency applications. I mean, Kafka is very fast, but it introduces latency. So Kafka, for those people not familiar with it, is actually written by LinkedIn in Scala, and it basically it's used by them to offload a lot of the processing of all their pages and other views. And there's something also called Kafka streams, which extends the basic concept, allowing for each stream to be partitioned and allocated stream tasks, which means it gives a sort of high level of asynchronous behaviour and parallelism. And there's something as well now that Amazon produced called Kinesis, which is an equivalent service, which is easier to set up, but it comes at a cost. It's kind of expensive. It's also has limits on how many messages you can send in 7 days, and also how long each message is retained. So actually, if you're not so bothered about latency, Kafka and Kinesis are actually really good choices for real-time data streaming and eventing. So if you need your messages for more than, say, 7 days and no limitation on message sizes, Kafka should probably be your choice, but it requires extra effort to set up, manage and support. However, though, Kinesis is catching up in terms of overall performance regarding throughput and events processing, but it's a new technology or newish technology, and it has a way to go yet. So we're going to have a little look at the eventing patterns we've been discussing. So there's orchestrated events. So if you are sending events onto an event bus or a message broker or a data streaming platform or whatever you want to call it, something in the background, another process is orchestrating those. So you have to write this orchestrator, and that includes retry and failure logic and things like that. You also have to pass the data in required to make any calls or publish an event each time, which can be bulky and be a lot of extra code to write. There are frameworks to do this for you, though. I think Twitter produced one, a number of other ones available. So really, the orchestrator. So think of the difference between the two, between orchestration and the next one is orchestration is like a conductor running an orchestra, whereas the next example I'm going to show you is choreography. Choreography doesn't need a separate orchestrator. It's like a set of people who dances. That's hence the analogy. The services manage their own interactions. So each service has to actually understand how to deal with what happens downstream through what events it needs to publish to. So it solves the problem of no out of process calls. It has no knowledge of other services other than it knows it needs to publish events. But what it doesn't do, neither of these really actually deal with unhappy path scenarios out of the box. So these both provide us this kind of wonderful decoupling and ability to work asynchronously. So that actually there is a pattern that can help us with this. It's called the Saga Pattern. It's a pretty old pattern. It was created in 1987. It's thought of nowadays as a microservices architectural pattern, but it predates them. It's basically a sequence of transactions, and each service, a Saga, performs its own transaction and publishes an event. So it fulfills that atomic requirement of a microservices. The other services listen to the event and perform their next local transaction. So far, it just sounds like orchestration or choreography. The main difference is, though, that you have to also have what we call a cancel Saga topic. So what happens with this is this builds in the idea that you have to be able to back out the entirety of a Saga, hence the name. So there's two types of Saga. There's orchestration-based Sagas. In this approach, there's a Saga orchestrator that manages all the transactions and directs the participant services to execute all these local transactions based on events. This is actually kind of a manager, which is called a Saga execution coordinator, kind of a lightweight workflow engine, and a workflow engines probably make people kind of shudder. But there's also a choreography-based Saga, so there's no external Saga execution coordinator. They manage themselves. But each Saga, each event, each service participating in the Saga has to also listen on the cancel Saga topic. So that means that they have to have that kind of built into them. So the main benefit of the Saga pattern is it helps maintain data consistency across multiple services without tight coupling, which is like really important for microservices architecture. But the main disadvantage is kind of the apparent complexity from a programming point of view. Also, developers are not really well accustomed to writing Sagas as traditional transactions. And also, you have to think about what we call the compensating transactions to make Sagas work. However, in my opinion, Sagas kind of help solve certain challenges and scenarios. Can be adopted if the need arises, but if you actually don't need a high level of kind of rolling back, if you're actually okay with it, there's something called what they call the Starbucks model, which is basically, in the case of failure, you just make sure you've got a really good logging and alerting platform in place, and you actually just go in and do manual intervention. And we call it the Starbucks model because if somebody messes up really badly, then the manager gets involved and then makes you a coffee and gives it to you for free, or gives you something, some kind of bonus card or something. So here's an example of the Saga pattern with compensating transactions choreographed, and you can see the service A, and it says, well, I've done my thing, and then service B tries to do its thing, and if actually service B fails, you can cancel the Saga. There's no point in service A sending a cancel Saga message really, because it's the first in the chain. Now, if you don't know where you will be in the chain, every single one will have to publish that event potentially, and basically all of the services in this listen to the cancel Saga event apart from the final one, because again, in theory, if the final one in the chain is done, then there is no cancel to be had. And what that means is each one of those then has to have its compensating transaction. But you can't confuse a compensating transaction with a rollback. There is no relational database transaction held open during these. So imagine if you're making a rollback on a database transaction, it's like it never happened. Whereas a compensating transaction is more like kind of a double entry bookkeeping thing, or say like a refund on a card. If somebody takes £50 out of your account by accident, it doesn't just get scrubbed. That transaction doesn't disappear. It doesn't get rolled back. It actually gets compensating transaction. Somebody gives you a refund, and then you see those two things. But actually, the end state is the same, but you end up with kind of more events in your store. However, all those Sagas often thought of kind of as a singular chain, and really it could become quite complex. There might be multiple concurrent consumers. They might publish multiple events. I mean, the actual chain can become quite complicated. This is a very simple example. And again, this doesn't really predicate that you use either a queue or a topic. In theory, you can do this with queues as well. If it's kind of a process once thing, then you can actually just use a queue instead. And coordinated Saga compensating transactions allows you to So this is using the AWS step functions, which is a web service that allows you to coordinate components of distributed applications and microservices using visual workflows. You build your applications from individual components, and they each perform like a discrete function. And this is actually like a really cool tool for it. So actually, rather than actually having to build up your own separate orchestrator, you can use something like the step function service to actually kind of create some simple coordination between them. So there were some other patterns as well that we needed to look at if we're going to be moving towards a more modern microservice approaches. Well, REST itself, REST is great for CRUD-based activity. If you just want to create, read, update, delete. But if you actually want business functionality, if you want something with workflow, REST doesn't really provide actions. Putting verbs in your REST APIs is kind of considered an anti-pattern, apart from the HTTP verbs, obviously. So CQRS, the command query responsibility segregation pattern, allows you to kind of use a more RPC style approach. So basically, you split out your queries, which is your read, kind of effectively your read models or your API aggregations, for your actual commands, which are the kind of do this, do that, your sort of verbiage. Now, CQRS is often used with something called event sourcing, and event sourcing is a really interesting concept that not a lot of people are currently implementing. Basically, instead of thinking of your data as kind of a flat point in time thing, you actually keep the list of events that have happened, list of things that have happened to your data over time. And since saving an event is a single operation, it's kind of inherently atomic. And what you do is, if you need to actually get state, you can replay the events. Now that sounds kind of processor intensive, but there's a couple of techniques we can use to get around that. So it kind of this event sourcing solves some of the has some several benefits. It solves one of the key problems in implementing event-driven architecture. It means you can reliably publish events whenever state changes. And because it persists events rather than domain objects, it kind of also gets around a bit of ORM impedance mismatch. It also provides a 100% reliable audit log of the changes made to a business entity. It means you can also do point-in-time queries as well. So if you want to see what the state of a particular item was at a particular time, you can just read your event store up to that point. It has several drawbacks. Well, firstly, it's a really unfamiliar style of programming, and you can obviously use libraries to help with it, but it's still it has a learning curve. People are used to just using either kind of NoSQL kind of flat document or a relational database. It's also difficult to query because you have to reconstruct the events. So some of the challenges, well, one of the things is if you've got a fully decoupled system, figuring out what the heck's going on can be actually fairly opaque. If you because events, things that publishers and subscribe to events can actually change freely. You can plug things in, you can plug new consumers in, and plug new publishers in. Actually, it can be very difficult to figure out what's going on. Orchestration can help that. If you actually use orchestration, that gives you more control over what's going on. But actually, if you're using distributed logging, if you're using something like Elk or Splunk or something like that, if you're using correlation ID with timestamps and time synchronization on your servers, actually, you can actually build up a picture quite quickly of what's going on in your system. So there are ways around that. The other thing is you can use what we call a consolidated event store. So the idea is reading a topic partition each time or a stream partition in Kafka each time is probably far too computationally complex. So we need a better way, and Kafka streams and state stores can be used to actually you can consume a number of topics, and what you can do is what we call event folding. You take the fold of all the events and then project them into what is effectively a read store, and you can keep that as a local store. So the good thing is about that is then you're not necessarily reliant on a downstream service. You can keep if you subscribe to the events, you can actually create your own local read store. So that means you are still decoupled. You can even do it in memory. Some people actually use in-memory databases to do projection. You might need a lot of memory to do that if it's a large database, but you can use a NoSQL database. And the good thing about that is if your read store dies, you can just rebuild it. Complex reads are also an interesting one because if everything's decoupled in its own data store, we want the information. We might be making hundreds of calls off a single page. Well, and REST is also just not great for aggregated reads, and you have to do a lot of wiring under the hood. But what we can do is use something like GraphQL, because GraphQL is great for API composition, but it's in itself will rely on things like using a consolidated read store, because you don't want to be doing a lot of GraphQL queries. And GraphQL, for those unfamiliar, is a Facebook technology which is used to get all their data. It helps us, and it allows us to retrieve just what we need when we're gathering data, and we've seen a lot of recent projects leverage it to make reads easier, but it kind of breaks the get caching out of the box with properly implemented REST, because most GraphQL calls are posted. You can use get, but it's pretty limited. So there are things like Apollo. Apollo provides a client-side cache, and things like Hasura and Stitch from MongoDB. Hasura works on Postgres that effectively automatically creates resolvers for you, so you don't have to write anything. Effectively, it automatically creates a read model for your database, and Stitch does much the same thing. So although it's a bit operationally convoluted, we can use something like KSQL to read Kafka streams, write them to Postgres or to Mongo, and then use Hasura or Stitch and GraphQL to provide a flexible read interface to the system, which is completely decoupled from your eventing, which is great. But even microservices are still very heavyweight. So one of the other things is, well, having to manage VMs is tiresome. Even containers can be heavier than we need. If we're performing simple actions, having a full JVM running somewhere just to read from a database seems like we're overkill in many cases. With cloud computing becoming more mature, we have a lighter weight solution, the serverless architecture. But why serverless? Well, it's pay as you go, so it's metered per millisecond. We can have close to zero cost depending on how much you're using. I mean, it can get very expensive if actually you're making many calls, so it's kind of a balancing act. If you're low traffic, then serverless makes perfect sense. If you're high traffic, you might want to consider managing your own services. It also scales pretty much infinitely. You don't have to deal with infrastructure or servers, so you can go from up to millions of requests, and it's not really a problem because the serverless platform basically scales automatically. AWS just handles in the background. Also means faster deployment. We don't have to manage VMs or manage JVMs or much configuration. You can effectively just deploy something like Node.js or Python code directly onto the platform. But GraphQL with serverless and some of the other technologies actually really actually gives us loads of flexibility. So using something like AWS Lambda or Azure Functions or Google Cloud Functions kind of makes life a lot easier. I'm going to show an example architecture. And this is sort of a very simple example architecture, very similar to what's been used by current client. And if you don't want to use Postgres, you can use Mongo and Stitch. But this basically separates the data streams. So I've used AWS Kinesis here, which you can just set up using a console. And if this meets your scaling and performance needs, this is a simple serverless Saga Pattern based architecture. It allows for fully decoupled operation, minimal coding, and near infinite scaling at the Lambda level. I mean, you can use containerized services to save on costs or SNS, things like that, or alternatives. But this is a kind of simple sort of example architecture showing that actually there's not too many moving parts to it. And it gives you a great read model as well as the ability to kind of put as many services in as you want. So I'm just going to time now for a couple of conclusions. So, I mean, right now, in the recruitment example I gave earlier, they've implemented eventing in GraphQL with minimal code. I mean, so we've seen these kind of things being used really effectively. But the Saga Pattern itself, it's a kind of an optimal target state, along with things like event sourcing, data streaming itself. If you don't need too much high performance, low latency, it can provide a great backbone. It can provide kind of an eventing and messaging as well as just moving data around. Using cloud native services, things like step functions, lambdas and kinesis, I mean, they can accelerate your adoption a lot. And you can move to heavyweight technologies later on if you want to. But you need to start thinking distributed, and that's really hard. You have to start kind of thinking more CAP theorem than ACID compliance. Transactional rollbacks are replaced with orchestration and coordination and compensating transactions. Your window into process flows becomes more opaque. So that means you have to put more effort into your design up front. But this is not design of your individual services, it's design of your platform. So you actually need to think about how data flows through your system more up front. It also means that actually you're producing a kind of a bigger architecture. You're going to have to think about having a good tech ops team, having a good DevOps process, because you're going to have more operational complexity. And of course, because you're building out more infrastructure, in theory, it could cost more than a monolith. It gives you all that agility. So I hope that's all I have for you today. I hope that was okay, and I'll be around for questions later on.